Okay, hello everybody. Thank you for joining again for today's ISGC seminar talk. Today's speaker is Christian Pfeifer from the ZARM at the University of Bremen. Christian did his PhD in 2013 at the Institute for Theoretical Physics at the University of Hamburg. And since 2020 now, he's a postdoc at ZARM. And with that, I hand over to Christian. Thank you very much for giving this talk today. And the stage is yours.
Yeah, thank you. First of all, let me thank all the organizers of this very nice seminar series for the invitation, and in particular Torben for contacting me. So I will talk today about teleparallel gravity, and I will give an overview over the subject. So there are many topics to be covered. I want to give you the broad overview, how we can describe gravity through torsion instead of curvature, if we like to. And in order to do that, I will introduce a bit of the mathematical notions in the beginning. Then later I will discuss how we can understand general relativity in terms of torsion instead of curvature. And then I will talk about modified gravity theories, which can be formulated in the teleparallel language. And as we said already for a few minutes ago, feel free to interrupt me anytime if you have any questions. I'm happy to discuss them. So let's start. One motivation for teleparallel gravity is to look at modifications of general relativity in a specific way. And so why should we be interested in modified gravity? Because we all know general relativity is very successful. So the Einstein equations, based on the Einstein equations, we can explain enormous amount of observables and features of gravity in the universe, like light bending, lensing by massive objects, shadow of black holes, the perihelion shift, gravitational waves, and the evolution of the universe as a whole, which has been demonstrated in particular in the last years in new observations made, for example, by Virgo LIGO or the Event Horizon Telescope. However, there are quite some shortcomings still in general relativity. When we look at the evolution of the universe and the rotation curves of galaxies, I guess this is very well known, that we must conclude that the universe consists of nearly 30% dark matter, nearly 70% dark energy, and then some baryonic matter. And if we then apply this to study the evolution of the universe, we nowadays find what is called the H0 and sigma 8 tension, that is deviating predictions for the Hubble expansion rate and the density fluctuations in the universe from different observations. On the theoretical side, also general relativity has some shortcomings, namely, so far there's no self-consistent theory of quantum gravity. Moreover, we have the inevitable prediction of the existence of singularities. And compared to all other forces, gravity is not formulated as a gauge theory. So in this sense, I think it's fair to say that general relativity and the standard model of particle physics are not the final understanding to our final answer to our understanding of the gravitational interaction. Now, the question appears, if it's not the final answer, what could be the final answer, or in which direction could we go? And we could either modify the standard model of particle physics or the description of gravity in terms of general relativity. And a few years ago, some colleagues created this map of modified gravity theories. So there are numerous ideas and suggestions how one could change the description of gravity, in which directions, and one can discuss a lot which one is the most promising path to take. In this talk, I want to look at teleparallel gravity, which is a reformulation of general relativity and then can be used to extend general relativity by changing the geometric description of space-time by going from what we know as pseudo-Riemannian space-time geometry, so space-time geometry described in terms of a metric, which then describes the gravitational interaction, and describing the space-time geometry in terms of torsion. That means we focus on this part of the map of modified gravity theories, that we look at metric-affine gravity theories, and the subset of that are teleparallel theories of gravity. And this brings me to a quick outline of my talk. So I want to first tell you what is teleparallel geometry, what's different to the usual geometric notion you know from general relativity to describe gravity. Then I will discuss the teleparallel formulation of general relativity before I discuss modified teleparallel theories of gravity and their phenomenology and come to my conclusion. So far for the introduction. So let us start with what is teleparallel geometry, what is different to the usual geometric setup we use to describe gravity in general relativity. And therefore, let me quickly recall, to bring everyone on the same page, what is affine geometry? So we look at a manifold, which is our space-time. We equip it with a tetrad, which has components theta and mu, and an independent connection defined by some connection coefficients. In this setup, for now, the metric is only a derived object. Yeah, these tetrads are interpreted as orthonormal frame of a metric, and the metric can be reconstructed with help of the Minkowski metric here. What we can think of as the Minkowski metric. So, and now a general connection can have in general very many different properties. So the connection defines the geometry of a manifold, and thus it defines how we describe gravity, as long as we identify gravity with the geometry of spacetime. And on the one hand, the connection can have torsion. That means it can have an antisymmetric part when I exchange these indices. This is usually set to 0 in general relativity. This is called the torsion tensor. Then it can have curvature. Oh, sorry, I wanted to say one thing more. The slides move faster than I want to. And the torsion, what it describes geometrically is when we do parallel transport along two vector fields along each other in different orders, it describes if this emerging shape, this emerging shape closes or not. Then we can have curvature. A connection can have curvature. Curvature is described by the usual expression for what we know as Riemann curvature tensor. In components, I write it here in components. And curvature describes what happens to a vector if I parallelly transport it around a loop, and then how much the original vector, the parallelly transported vector, differs from the original vector. And last but not least, if I have a metric on my space-time, the connection can be metric compatible or not. So the covariant derivative of the metric can be 0 or non-zero. This is called the non-metricity. And this non-metricity measures how much the length of vectors changes if I parallel transport them along a path. And now there's a mathematical theorem that given an arbitrary connection, I can decompose it into a part. If I have a metric, I can decompose it into a part which is the Levi-Civita connection of the metric. It's given by the Christoffel symbols, completely determined by the metric. Then a part which is called the contorsion tensor, which is solely determined by the torsion property of the connection, and the part which is called the disformation, which is solely determined by the non-metricity. And if you look in papers and literature on metric affine geometry, or metric affine gravity, then these two terms, the contorsion and the disformation, are together combined to a tensor that's called the distortion. So, and if you're interested into gravity theories built on a general metric affine geometry, basically what I outlined here, I can recommend this nice review by Hale and collaborators on metric affine gauge theories of gravity. So now these general geometries have certain subclasses, and we are interested in these subclasses. So when we look at Riemannian geometry, the formulation on which general relativity is based, the geometry on which general relativity is based, we set the torsion and the non-metricity to 0 and work with the Levi-Civita connection, where then the connection is just given by the part which is uniquely determined by the metric that has no torsion and no non-metricity. Then we could look at so-called Einstein-Cartan geometry. These are geometries where we have no non-metricity, so the connection is metric compatible, but has torsion and curvature. Then for us today, most interesting is teleparallel geometry, where we only work with torsion and look at a connection that is flat, is metric compatible, but has torsion. And last but not least, one could also look at a space-time geometry which is solely based on non-metricity. This is what one calls a symmetric teleparallel geometry. And also there are gravity theories and modifications of general relativity which use this property. We will encounter this later again. So now let us focus on the...
May I ask a question?
Yes, yes.
Okay. I'm wondering, do you need to equate the manifold with a derivative operator?
Yeah, I mean, when you have a connection, you can define, you automatically get a covariant derivative.
Okay.
Yeah.
So this sense is it is not necessary to equate the derivative operator.
No, you get, so when you have a connection, you have a covariant derivative.
Yes, I see. Okay, okay. Okay. I see. In this sense, thank you. I see.
Okay, thank you. So now, what are the properties if we restrict ourselves to the teleparallel geometry? There, as geometric fields, we take the tetrad as our fundamental variable. We take an independent flat and metric compatible connection, as I already said. And the metric we consider as a derived object, which we can derive if it suits us, but we don't need necessarily to. And then the connection can be expressed in the tetrad basis in this form, which is given by the derivatives of the tetrad and its inverse. So this object here is the inverse tetrad. And an object that's called the spin connection, and is just given then by this can be decomposed into a Levi-Civita part plus some correction here in terms of the contorsion tensor. And now if we demand that such a connection is metric compatible, flat, and has torsion, then there is a requirement on the spin connection here, this omega, the spin connection coefficients or Lorentz connection coefficients, namely that they are generated by Lorentz transformations. So we could write down such a connection here. This is fairly general. It's basically a covariant derivative of the tetrad. And here are some connection coefficients. But then imposing flatness and metric compatibility implies that the spin connection is generated by Lorentz transformations. Yeah? So these lambdas here are exactly objects of the Lorentz group. And this leads then to the next important observation when we discuss teleparallel gravity and geometry, namely that we can study what happens if we perform a Lorentz transformation on the tetrad. And the following happens. So we apply a Lorentz transformation to the tetrad to get a new tetrad. We do the same for the inverse. And also we do a Lorentz transformation on the original Lorentz transformation matrix, which generated our spin connection in the following way. Then what one can calculate is that the metric and the affine connection coefficients here, that they are invariant under such transformations. Yeah, the spin connection not, but the spin connection is exactly introduced so that the metric and the affine connection coefficients here are invariant. And now we can choose a very specific transformation, namely by choosing this transformation matrix here, the Lorentz transformations, as inverse of the original Lorentz matrix which generated our original spin connection or Lorentz correction. And then what we get is, when we calculate the transformation behavior, that the spin connection coefficients become 0. The affine connection is just the derivative of the tetrad, and the torsion is also given just by antisymmetric derivative of the tetrad, a first derivative. This is what's called the Weizenbeck gauge. This is a gauge fixing. So I fix a certain Lorentz frame in which I work, but nevertheless, this whole theory is invariant under these transformations, because I can always reintroduce a spin connection. I now just work in a very specific frame, so for a very specific choice of tetrad and Lorentz matrix, actually, because instead of working with the connection, I can always work with one of the Lorentz matrices, where I fixed my Lorentz matrix. It's not a degree of freedom anymore. So all degrees of freedom now, which I want to later determine by gravitational field equations, are encoded in the tetrad. So, okay, so this is a setup, and my gravitational field, so gravity will be encoded in the tetrad, and the torsion is something from the torsion I can construct something like a kinetic term for the tetrad. And having in mind that I can always reconstruct the spin connection by applying Lorentz transformation, this is a way to make the theory Lorentz invariant. Yeah, so basically to remove the gauge fixing. And then if I want to solve the field equations later in teleparallel gravity, I need a notion of symmetry. Yeah? Usually when we solve the Einstein equations, we consider spherically symmetric solutions to describe black holes, or axial symmetric solutions, or we consider homogeneous and isotropic solutions in order to describe cosmology. So how do I describe symmetries? Symmetries in general are some transformations which preserve the geometry. So I have a map from my manifold to my manifold where I let a Lie group act on my manifold and on all my geometric objects. And I want that they are invariant in a certain sense. And therefore, I find generalized Killing equations in the Weizenberg gauge, namely that the Lie derivative of my tetrad must not be zero, but must be zero up to a generator of a Lorentz transformation, and the Lie derivative of my spin connection, that must really be zero. So these generators of the Lorentz transformations I can consider here. The freedom I have is restricted to constant generators, which don't depend on the space-time point. And so X are so these vector fields X are the Killing vector fields for teleparallel gravity. And yeah, as I said already, lambda is a generator of a Lorentz transformation that is compatible with this group action. I do not want to get into more detail here. It's just to let you know we can find symmetric tetrads and spin connections. So yeah, spin connections and tetrads which have a certain symmetry property. And in a nutshell, maybe I hope I have not lost anyone yet. But in a nutshell, you can think about teleparallel geometry as a geometry that is constructed from tetrads, a flat and metric compatible spin connection with torsion. The metric is a derived object. And then there's one important identity, since this connection here is flat, and we can always decompose this flat connection into a Levi-Civita and a contortion part, we can derive the curvature of this general connection and expand it into the curvature of the Levi-Civita connection plus correction terms. And this is the formula you get. So if we want, we can always rewrite derivatives of the contortion into the usual Levi-Civita curvature tensor or the usual Levi-Civita curvature tensor into covariant derivatives acting on the contortion. This is a mathematical identity which we may need later from time to time.
Christian, can I ask you a question?
Yes.
On the left, on the left third of your background slide, you have two connections, gamma and omega.
Yes.
Gamma and omega. They're both connections on the tangent bundle of your manifold.
Yes.
Right? As such, not talking about coordinates, as such, connections on the tangent bundle. Are they the same or they're different?
I mean, they are the connection coefficients in different bases, basically. Yes. So I can express my connection coefficient. The connection is the same. It's defined. I can define my connection in a coordinate basis, or this is basically the connection in the frame basis. And these tetrads, they act as they solder together the tangent bundle and the frame bundle to the tangent spaces. Yes.
But they are the same connections, right?
Yeah, they're the same connection. Yes.
Okay. And I also got confused because you said the connection in the tetrad basis, but you write it down in terms of Greek indices. So that
Greek indices are my coordinate indices.
Yes.
So this gamma, sigma, mu, this is meant to be in coordinate indices. Maybe it becomes more clear here. Here, this is how I define my indices. Yeah, I have tetrads and tetrad indices, which I label with 0, 1, 2, 3, which are which are just numbering the tetrad, and the Greek indices are labeling the coordinates. Yes.
Yeah, but why do you write tetrad basis? I mean, it's a connection in the coordinate basis, not in the tetrad basis.
Disaster.
Yeah.
Right. Thank you. I'm sorry. The connection in the tetrad basis would be the omega. Yes. Okay.
Exactly.
Yes. I'm sorry.
Okay.
Yes. Thank you for pointing this out. This is a mistake. This must be coordinate basis or the affine connection coefficients.
Yeah.
Yes. Yeah,
okay,
sorry.
Thank you.
My apologies. Further questions? Okay, so this is our foundation with which we now want to describe gravity. And now it's interesting that we can first of all formulate general relativity using the torsion as well as using curvature. And therefore, let us recall that there exist actually three geometries, kind of natural geometries in which we can formulate general relativity, and how we can write down the field equations and the meta-coupling for these different geometries. So what one can do is one can consider this following Lagrangian, which is just given by the Christoffel symbols of the Levi-Civita connection. And this Lagrangian, called the Einstein Lagrangian, if you do variation with respect to the metric, you get the Einstein equations. It's not the Einstein-Hilbert action, it's something different. Yes, here, this is not the curvature. The caveat with this action is it is not covariant. The the expression here under the integral is manifestly not covariant. And the question is, how can we make this covariant? And there are three ways how to do this. So we can add three boundary terms to covariantize this action manifestly. And the first one is to add one boundary term to get the Einstein-Hilbert action. So there exists a certain boundary term. I will tell you how it looks like in a moment, which we can add here and to get the usual Einstein-Hilbert action, which we know. Then there is another boundary term which we can add, which gives us the so-called teleparallel equivalent of general relativity. So instead of using this identity we had on the previous slide between the curvature tensor and the contortion tensor and its derivatives, one can show that the Riemann tensor, if I subtract or add a certain boundary term formulated in terms of the torsion, this 2 is I think this 2 is wrong. Sorry. Yeah, the 2 should be maybe here. Okay, there's a factor wrong here. I'm sorry. In order to formulate this action completely, not in terms of the metric, but in terms of the torsion tensor generated by the tetrad. Yeah, we are using a geometric identity here. And then you can also immediately, since we know how the Riemann, the Ricci scalar is related to the Einstein-Lagrangian, then also this object here is related to the Einstein-Lagrangian just by another boundary term. And we can do the same for the non-metricity connection. There's a similar equation as I showed you for the contortion, for the distortion, for the non-metricity parts, and also the action can be formulated. The Einstein action or the Einstein-Hilbert action can be formulated equivalent up to a boundary term completely in terms of this connection which has non-metricity and no torsion and no curvature. And all of these three theories, they are dynamically equivalent in the sense that when you do variation with respect to the dynamical variable, you get the Einstein equations. Maybe formulated in terms of different tensors or different tensors with different geometric interpretation, but the solutions you get are the same. Sometimes in this paper by Beltran and Jimenez, Koivisto and Heisenberg, they called this the geometric trinity of gravity, which they summarize in this nice triangle. So you can formulate general relativity in terms of tetrads and torsion, metric and curvature, or metric and non-metricity. And all the time you get the same theories, even though the underlying geometry has a completely different interpretation. So we focus on this teleparallel equivalent of general relativity. And so now what is this T? Therefore, to understand this T, this is a specific, what we call the torsion scalar. And in order to construct it, we decompose the torsion tensor into a vector part, into an axial part, which is antisymmetric, an axial part, which is constructed with the Levi-Civita tensor here, and the remaining tensorial part. These can be combined into what is called the vector torsion scalar, the axial torsion scalar, and the tensor torsion scalar. And they can be combined in this very specific way with these very specific coefficients. And this is, again, a mathematical identity that you can show that when you take this formula from the which relates the contortion to the curvature, you get this combination. And this is what's called the torsion scalar, which is the Lagrangian for general relativity expressed in terms of torsion generated by a tetrad. And then we can calculate the field equations. We do variation with respect to the tetrads. We manipulate the field equations. We get some energy momentum tensor from variation of the matter action. And we get, in general, symmetric and antisymmetric field equations. And for the teleparallel equivalent of GR, one finds that this left-hand side, this antisymmetric part of the field equations vanishes identically. So what is missing is how do we get the meta coupling? And there are two choices. I can couple my meta fields, scalar fields, spinors, electromagnetic fields, so vector fields, either to the teleparallel connection or to the Levi-Civita connection. This is basically a choice I have. And if I do this, then I find that if I couple the meta to the Levi-Civita connection, where actually, when we impose minimal coupling procedure, only spinors couple to the connection. You don't need a connection to write down the usual action for scalar fields and electromagnetic fields. Then when we just couple to the Levi-Civita connection, we find the antisymmetric part of the energy momentum tensor vanishes, while if we couple to the teleparallel connection, and it's really present in the action, the connection coefficients, then we find the antisymmetric part of the energy momentum tensor does not vanish. And this leads to the following consequences in the teleparallel formulation of GR, that it dynamically selects that we can have no coupling between the fields and so spinors and the teleparallel connection, since in the teleparallel equivalent of general relativity, the symmetric part of the field equations are really just the usual Einstein equations with the usual energy momentum tensor. But the antisymmetric part of the field equations, the left-hand side is automatically 0, so the right-hand side must be. And this is then a constraint on how matter can couple to the geometric features. In modified teleparallel gravity theories beyond general relativity, this is not necessary. However, for the coupling, this is not necessary. And we can summarize this by saying that the metric matter coupling is selected dynamically in the teleparallel equivalent of general relativity. And yes, so let's sum this quickly up. In a nutshell, the teleparallel formulation of general relativity, we can use this identity, this relation between torsion and Levi-Civita curvature to calculate this. I'm really sorry, I forgot the factor of 1/2 or 2 here somewhere. We get this relation up to a factor between the Ricci scalar and the torsion scalar. And the difference is exactly a boundary term, so they are dynamically equivalent. The same we can do for the symmetric teleparallel of general relativity, and the matter coupling dynamically enforces that this coupling to the Levi-Civita connection of the matter. Yes, this summarizes the teleparallel description of general relativity.
Okay, could you please explain a little bit more to how did you calculate the number of the degrees of freedom of these 3 kind of theories?
Okay.
Yeah. You showed
so
a picture before.
Yeah. So here in the teleparallel case we have in principle 16 degrees of freedom, which are in the tetrad. Then we have 6 Lorentz transformations, the Lorentz symmetry, which go off. And this would give you then the usual 10 metric degrees of freedom. And then this means propagating degrees of freedom here. Yeah. Then you still have to do the constraint analysis, and you find that in the end you have 2 propagating degrees of freedom. So
the six constraint, they are the second class constraint coming from the Lorentzian symmetry.
Yeah.
But symmetry is usually related to the first class constraint. But why do they are the second class? Why? Yeah.
I remember having done this calculation, but it's quite some time ago. So you can do the Hamilton analysis of the theory, and you see it. This is it in a nutshell. It's not very satisfying answer, I see.
Yeah. Okay.
But I would have to look it up where exactly it appears and how it enters.
Yeah, and as best as I note, the Hamiltonian analysis formalism to the non-metricity theory is not really cleared yet.
Yes, that's under construction. Yeah, but for the teleparallel equivalent of GR, it's definitely done.
Okay. Oh, thank you very much.
Yeah, you're welcome. Okay. Yes, so in principle, some people sometimes say maybe if general relativity would have been formulated after the emergence of particle physics, it would have been formulated in terms of torsion instead of curvature, since this looks a bit more like a standard gauge theory because you have some vector fields, you take the exterior derivatives, and this torsion can be interpreted as a field strength of the translation group. I will not go into the details here, but and also, I mean, it didn't happen this way, but this is what is sometimes philosophized. Okay, and now we can use this to discuss field theories and modifications of general relativity. So let us look at modified theories of gravity and teleparallel theories of gravity and their phenomenology. So let's go beyond the teleparallel equivalent of general relativity, and that means considering an action with some meta-coupling of the torsion tensor, where we construct a scalar of the torsion, the derivatives of the torsion tensor, and maybe higher order derivatives. We can in principle construct any scalar invariant we like. Then when we do calculate the field equations for the tetrads, we get a symmetric part and an antisymmetric part of the field equations in general. And what is nice is that as long as this scalar we construct just depends on the torsion and not on its derivatives, we always get second order field equations. So there's no Lovelock theorem. This is why the variety of modified teleparallel theories of gravity in 4 dimensions is way larger than the one which we can construct with curvature invariance, only with curvature invariance, because in the metric and curvature formulation, we have the Lovelock theorem. Then the building blocks, I just showed you already, the building blocks to construct these scalars from the torsion tensor are the vector torsion, axial torsion, and tensor torsion. And from this, we can form 3 quadratic parity-even torsion scalar invariants, the vector torsion, the axial torsion, and the tensor torsion. You already encountered this. And one can discuss 2 parity-odd torsion scalar invariants, which are constructed from a contraction of the axial and vector torsion, and from an antisymmetric product, so to say, of the tensor torsion. And with this, we can look at, and in principle, we can construct any scalar theory and scalar Lagrangian from these invariants we like, with or parity odd, parity even, or products of parity odd terms to get something parity even again, we like. And I want to show you now some most prominent theories in the literature, because you can already imagine the variety is vast. For example, one could look at what's called new general relativity, or one parameter new general relativity. That is looking at the most general quadratic parity even torsion scalar you can form, and that is this one, and that is parametrized by three parameters, CV, CA, CT, which for general relativity take a very specific value, which we had on the previous slide. And this theory has been suggested a long time ago. I will discuss it a bit further in a moment. And very often one reduces it to a theory where one only has 2 parameters. Another possibility is to do an axion coupling. So coupling in a very natural way torsion, axions to torsion, because we have this parity even scalar invariance, quadratic scalar torsion invariance. We can couple here 2 axions, for example, to axion scalar fields to these in order to get some parity even generalization of new general relativity. And since general relativity is a part of that, it's a very natural way to couple axions to the geometry of space-time. Then one could look at f of t gravity, or what's called f of tb gravity, where this b is this boundary term which connects the Ricci scalar to the torsion scalar, and these are generalizations then of f of r gravity theories. And also here the variety which you can look at is simply larger, since you can consider the torsion scalar and the boundary term separately. Then there's one very famous, or the most famous, one most famous theory is f of t gravity, is a Born-Infeld f of t gravity, where one considers a Lagrangian of this form, which is loosely related to the Born-Infeld theory of electrodynamics. And with this theory, people studied inflation and proved that one can also describe inflationary periods of the universe in terms of teleparallel gravity. Then we can couple extra scalar fields analogously to scalar tensor theories. We can look at scalar torsion theories and look for scalarized black holes and similar things. We can look at the teleparallel Gauss-Bonnet theory here. One can show that the usual Gauss-Bonnet invariant boundary term in 4 dimensions as a boundary term decays in the teleparallel language into 2 boundary terms, which again can be coupled separately to a scalar field. So the general observation is that when we use torsion and the teleparallel formulation of space-time geometry, that we have a finer ingredients to construct gravity theory. And then some colleagues also looked at what's called teleparallel Hondesky theory. I don't know if you are familiar with Hondesky gravity. That is the most general scalar tensor Lagrangian with second-order derivative field equations. And this can similarly be studied in the teleparallel language. Now, this is just a very rough overview over many, many theories. And now I want to go in detail into some of the theories and discuss a bit of the phenomenology that has been discovered in the recent years. And in the end of the talk, there's a long bibliography, since the space is too small to list all of the papers here. Please be patient in this regard for the end.
Sorry for so many questions.
No worries. I'm happy for questions.
Okay. What do you mean the second order if f equal to ft, no Lovelock theorem?
So we have second order field equations for the tetrad. Since the torsion has a first derivative in the tetrad, if you take any function of that and you do variation and you do integration by parts, your field theories will be second order derivatives acting on the tetrad.
Okay. So
and
please.
And when you do this for the metric, if you look at metric theories of gravity formulated through the curvature, we know by the Lovelock theorem that in 4 dimensions, there's only the Einstein-Hilbert Lagrangian plus cosmological constant, which leads to, if we only consider the metric as dynamical field, similarly as we only consider the tetrad here, when we only consider the tetrad here, then this is the only choice in 4 dimensions to get second order derivative field equations for the metric.
So you mean there is some similar theorem for the tetrad theory?
No, there's no.
There's no.
This is no Lovelock theorem. This should okay. Maybe I should highlight this more.
Okay.
If this scalar which we construct, the torsion scalar, is any function just of the torsion, not of the derivative of the torsions. So if no derivative of the torsion appear, then we always have second order field equations. These field equations, they're always second order.
But the second order field equation, there are so many possibilities to derive the. Okay.
Yeah. Many.
So do you think there's a similar theorem to the tetrad theory, similar to the Lovelock theorem?
No, there is none. There's none.
Oh, okay. Thank you.
So, Christian, may I ask another question? So,
yes, sure.
Is this true also for non-metricity theory? I mean, the equation of motion are always second order, or in general?
Yes, because also the non-metricity, if you start with the non-metricity tensor, that's the first derivative on the metric. So for the metric, you always get, if you don't have derivatives of the non-metricity tensor in your theory, you always get second order derivatives. Yes, I think so, yes.
I see. Thank you.
Okay, thanks for the questions. Then now let us, so I have several topics on the most, let's say, most studied, so this is a non-complete list of gravity theories. I now pick 3 gravity theories beyond general relativity, 3 teleparallel gravity theories beyond general relativity, which are the ones where also I work the most on and most people work on, to my knowledge, but they are not, this is not exclusive. Yeah, there are many people working on all of these theories. And that is new general relativity, f of t gravity, and scalar torsion gravity. I don't know if I make it through all of them. If you're interested in some of these theories in particular, I can jump to that section. I would now start with new general relativity, mainly because it's the simplest and the one which is closest to general relativity. So then how is a new general relativity defined? It is defined by a 3-parameter Lagrangian, which is the most general quadratic parity even torsion scalar. Some of them, parity even torsion scalars, what you can construct. And this has been introduced quite some time ago already, and also studied since then a long time. And this general theory is highly constrained, since already when you calculate perturbative spherically symmetric solutions here around general relativity, you find strong constraints. What you find when you study perturbation theory here, that symmetric and antisymmetric modes couple, and this always leads to inconsistencies in field theory. And also what you find is that perturbations around Minkowski spacetime are not stable. So if you have Minkowski spacetime do perturbations, you're not going back to Minkowski spacetime. So this theory in general is mathematically maybe interesting, but physically certainly not viable. What one can study is a subclass that's called one-parameter new general relativity, where one fixes two of these coefficients to the value they have for the teleparallel equivalent of general relativity, and considers a deviation only in the axial torsion coupling here. And then I do not display the field equations here in general because they are very, very long for all of these theories. You can check them in the paper, or if you are interested, we can also discuss about them. But yeah, just to give you a flavor how teleparallel gravity vacuum field equations look like, I show them here for this one-parameter new general relativity, which can be rewritten in this nice form. You have symmetric field equations, which contain a correction to the Einstein equations in terms of the axial torsion. And you have antisymmetric field equations, which are solely sourced by this perturbation. And both of them you have to solve. These are 10 plus 6, 16 field equations. In principle, we have 16 fields in the tetrad, and so we need to solve these equations. This model is currently very weakly constrained by observations. It has some interesting features, as we will see in a moment, which give potential to constrain them. Then one can show that, for example, Kerr spacetime, if we choose a certain tetrad of Kerr spacetime, this equation is solved. Since Kerr spacetime possesses a tetrad whose torsion has no axial torsion, and then for such tetrads, if we can have a solution of the Einstein equation for a metric with a tetrad that has no axial torsion, then we have a solution of these field equations. The PPN parameters here are S in general relativity of this theory. And we find new black hole solutions beyond general relativity. This I want to discuss in some detail in a moment. And what we find is when we do perturbation theory in cosmology, we find that on curved Friedmann-Lemaitre, Robertson-Walker backgrounds, we find gravitational wave birefringence. This would be one option how to constrain these models. So let me discuss these predictions in a bit more detail. But in order to find black holes in the theory, I need an ansatz, a spherically symmetric ansatz. And that's why I discussed the symmetry conditions in the beginning. If I impose spherical symmetry, so I impose the existence of three killing vector fields on my space-time, which generate the spatial spherical symmetry, I get that the most general spherically symmetric tetrad has this form. It is described by four free functions, A, B, alpha, and beta, which are general functions of T and R, which lead to the metric here, which you know is the most general spherically symmetric metric. Right, and we see that we have two metric degrees of freedom, which appear in the metric, and we have two pure tetrad degrees of freedom, this functions alpha and beta. And now if you put this in the field equations, one gets from solving the antisymmetric field equations, we get basically determine the alpha and beta, and then the remaining metric field equations shall determine A and B. And this can be done. And we get three classes of solutions. The first one is rather boring. We choose alpha such that sine alpha is 0 and an arbitrary beta, so beta is not fixed, this tetrad degree of freedom. And we get that only the Schwarzschild metric solves these field equations. Then the more interesting class is when sine alpha is not 0, but alpha is still a constant, then we can uniquely determine beta as a function of the metric coefficient, the radius, and this now constant alpha, and we get that the T component of the metric is given by the usual Schwarzschild expression, but the RR component gets a modification here, which is sourced by the coefficients of the theory. And then for the most general case, we only have an incomplete classification. We could not solve the field equations if we don't assume the alpha is constant. We find that under certain conditions, namely assuming that A is equal to the inverse of B, then only Schwarzschild solves, and alpha and beta can be determined but don't play a further role. However, if we do not assume this, there might more general solution exist. But in this sense, what we find here that one parameter new general relativity allows for a teleparallel black hole generalization, an analytic generalization of the Schwarzschild geometry, which is predicted by this theory. The theory, and let me abbreviate this denominator here just by h for now, just to simplify the notation.
Sorry, can I ask a question?
Yeah, sure.
Is this three solutions connected by some coordinate transformations, or
No.
so? Are this alpha and beta is like some gauge choice, or?
No, alpha and beta. So we fixed our gauge, so we cannot do any Lorentz transformation anymore. We fixed our coordinate system. So originally, when you solve the symmetry condition, you get 6 free functions in the tetrad. And then we do a coordinate fixing that we fix this expression here to r squared, and we remove the cross terms in dt and dr. This fixes our coordinates on space-time. And the Lorentz transformations, we have already fixed the Lorentz frame since we are working in Weizenberg gauge. So we solved these equations with vanishing spin connection. So this is completely fixed. These are really 3 different branches of solutions.
I see. Okay.
I mean, they're parametrized by the value of alpha, basically. Yeah. If we assume alpha is 0, then we get Schwarzschild. If we assume alpha is any constant such that sine alpha is non-zero, here you see it. If cosine of 2 alpha is this is 1, then we are back to Schwarzschild. No, wait, no, that's wrong. You see that here is a condition. Sorry, that was right. If cosine of 2 alpha is 1, then this term vanishes, and we have b is a to the minus 1, then we are back to Schwarzschild, then we are exactly in this condition. And here, this is again a Schwarzschild solution, but we don't know if more general solutions exist. And most likely they do, just the equations are more complicated to solve.
So basically from the equations of motions, we cannot see or solve alpha and beta. So we have to pick some, so we have to pick or fix the value of, or the functions of alpha and beta.
We make, when you look at the antisymmetric equations, you see that there are these different, that you can decompose them in these different branches. You see definitely that sine alpha equals 0 solves the antisymmetric field equations immediately. You see that if sine alpha is not 0, but alpha is constant, and beta takes this form, then then you can determine beta, and then you can solve the symmetric field equations for A and B. And in general, here, when you make the assumption that A is 1 over B, then you also see that in general, you only can have the Schwarzschild solution. Yeah.
I see. Okay, right.
This is not the most, this is not the most general solution. This I cannot claim since we haven't found it yet. So here, this is what I mean with incomplete classification. Yeah. And also you see, certainly there is no Birkhoff theorem or something like that. We get here many parameter family of solutions. So, so it's not that there is a unique spherically symmetric solution here. Asymptotic.
One question.
Yeah.
So in general, can we say that the TEGR solution space of the TEGR is bigger than the Einstein gravity, or?
No, for TEGR, it's identical.
TEGR is identical to Einstein gravity?
Yeah. For the metric, if you derive, no, it's identical. Yes, when you
but you show that in the case of the black hole looking like solutions, you seems to have more solutions.
Yeah, because we are not in the TEGR case. We are here in the one parameter new general relativity case, where we have that this axial torsion coefficient is the TEGR value plus some correction, this zeta. So this is basically left arbitrary. That's why it's called one parameter new general relativity. And that's why these field equations are modified by this zeta. Yeah? If I let zeta go to 0, I'm in the GR case. And if I let zeta go to 0 in my solution here, I'm back in the Schwarzschild solution in all cases. So then I'm back to the Birkhoff theorem. So it's really this deviation from TEGR which gives us new solutions.
Okay, thank you.
Right. Okay, and then what we need to impose here, this h is a function of the model parameters, so this zeta and alpha. We need that this h is positive in order to have a Lorentzian metric signature. What we also found is that this metric is non-asymptotically flat. You see that you have a component of the Ricci tensor, which is not scaling with the radius. So it's constant if you let R go to infinity. What is interesting, since what we need to check is if a Birkhoff theorem works, it's a very nice thought for asymptotically flat black holes. We haven't checked that. Yes, and this is basically what characterizes this solution. And now we can, in order to constrain these solutions a bit more, we can basically, in quotation marks, turn the crank and look at classical observables like perihelion shift, light deflection, the Shapiro delay, or black hole shadows, or any other observable you like. So let's look at the perihelion shift, for example, comparing it with comparing the prediction with what is observed around the star, what is observed in the stars orbiting Sagittarius A star. And there we get that the perihelion shift is proportional to the perihelion shift you predict with the Schwarzschild metric, modified with this function h here, and you get a modified offset here. A similar expression you find for the light deflection angle here, which quantifies the gravitational lensing effects. You get a rescaled Schwarzschild expression plus a correction. And the same is correct for the Shapiro, and the same similar structure you find for the Shapiro delay, which one can, for example, use in pulsar timing and compare with pulsar timing predictions, where you again get a teleparallel correction. And these would be observables with which we can constrain this model. Also, we calculated the impact on black hole shadows, where we find that the size of the black hole changes for a given mass when we modify this function h. And all these observations give us constraints on our model parameter, on our teleparallel correction to general relativity. And it's currently work in progress to really do this numerically and properly to find good constraints. So this is one class. Yes?
Yeah, roughly at 50 minutes.
Yeah. Okay. So then let us continue. So these are constraints and effects you find from teleparallel modifications of general relativity in spherical symmetry. Let us switch quickly to cosmology. So let us look at homogeneous and isotropic, so cosmologically symmetric tetrads. And there we find two tetrads of the Friedmann-Lemaitre-Robertson-Walker metric, which solve the antisymmetric field equations. One class we call the vector tetrad, another one the axial tetrad. They were found by Manuel Hohmann. And when we now, so the vector tetrad does not lead to interesting phenomenology, but the axial tetrad, if we now calculate perturbations of this tetrad and study their propagation of the symmetric and trace-free part of this perturbation, from the field equations, we find a dispersion which is different for different polarizations of the symmetric trace-free part. And they are influenced on the one hand by the theory parameter zeta, and on the other hand by this curvature parameter. So this u is square root of the curvature parameter, and this curvature parameter can be 0, 1, or -1, depending if we are looking at a spatially closed, open, or flat universe. And when we derive the propagation velocity, so phase and group velocity of this tensor perturbations here, we find that the different polarizations have a different propagation speed. So this is gravitational wave birefringence. This k is the wave covector of the gravitational wave. And we see that for flat Friedmann-Lemaitre-Robertson-Walker spacetime, we don't see such birefringence, but only for the curvature. That means if we measure the speed of gravitational waves of the different polarizations and find the birefringence there, a difference there, this could hint for such a modification. Yes, okay. This concludes the discussion of new general relativity, and to give you a flavor of what one can do with torsion, with theories, with teleparallel gravity theories beyond general relativity. So now we already reached the 55 minutes. I have two more topics, and it depends on now. I would suggest that jump to scalar torsion gravity because that's a bit more interesting than f of t gravity, in my opinion. If that's okay, I would quickly discuss some features there and then conclude. Or should I stop here?
How long would you need?
Don't know. 5 to 10 minutes. For
I
scalar
think then
torsion
it's
gravity,
okay.
maybe 5, and f of t gravity I can also do in 5. Okay, then I do both. So f of t gravity is the canonical generalization of f of r gravity in the Teleparallel framework. It's defined as taking as Lagrangian any function of this torsion scalar, and the idea was to describe inflation without needing the need of an additional scalar field. And this has been done in this paper here. And since then, this theory also has been studied a lot. A lot of applications to cosmology exist. What is unclear here also is the number of propagating degrees of freedom. The Hamilton analysis of general f of t gravity is surprisingly cumbersome. Many models possess so-called ghost modes, so ghosts with non-proper or non-causal propagation behavior. And my latest knowledge is still that there are different papers claiming different numbers of degrees of freedom. I'm not aware if this has been resolved by now, but there's still many people working on that. So, and then the question surely is, which one is the best choice of f? Originally, in this paper, the Born-Infeld teleparallel gravity was considered. And then what one can always consider is a perturbative expansion. What do you get as first-order corrections? Or we can also consider f of t b gravity, which would be the generalization really of, since t and b can always be combined to a Ricci scalar, this is a generalization of f of r gravity. Which leaves us with more possibilities, because this Lagrangian cannot be reduced to an f of r Lagrangian except these coefficients in front of t and b satisfy a certain constraint. Okay, here we can also describe results. So we can perturbatively again try to find solutions which perturb the Schwarzschild solution and calculate the classical observables like the perihelion shift, the diameter of black holes, and light deflection. What is interesting also that we could find here non-perturbative black holes for Born-Infeld gravity. And it has been presented that there exist non-singular black hole interior solutions. And we find also non-singular interior solutions and non-perturbative black hole solutions for outside the horizon, and the one question is still if one can merge them. And the solution, the non-perturbative teleparallel black hole, it's the only one in f of t gravity for Born-Infeld gravity, which is non-perturbative to my knowledge, takes this form that we have the theory parameters lambda, and that we have this tangent correction here. And in the weak field limit, we find from the post-Newtonian analysis, so to say, that lambda must be larger than 140. And we also derived the shape of accretion disks, where one sees here with the same parameters, the accretion disk model for a Schwarzschild black hole, and then modifications due to the lambda, to the teleparallel modification. Okay, then last but not least, very quickly, maybe also scalar torsion theory. They are so here we couple an additional scalar field together with its kinetic term to the torsion scalar and the boundary term. This generalizes the usual scalar tensor theories. They were introduced to model teleparallel dark energy with an inflaton. One can study teleparallel boson stars. I already mentioned this teleparallel Rondeski theory. And one can study if torsion, these boundary terms of torsion, maybe lead to scalarized black holes, similarly as the usual Gauss-Bonnet term, when coupled to a scalar field, leads to scalarized black holes. A simple model for a non-minimal coupling is looking at the torsion tensor, torsion scalar with an arbitrary scalar coupling function, the kinetic term of the scalar field with an arbitrary coupling function, the boundary term with a coupling function, and a potential. And in this model, we are back to a scalar tensor theory if the A is equal to -c, since then we can combine the T and the B to the Ricci scalar. And what is interesting that for some choices of A, B, C, and V, we find exact solutions we find quite some exact solutions of black holes with scalar fields, but most of them are not asymptotically flat. But there are two subclasses which are actually asymptotically flat. And again, we use the usual spherically symmetric form for the metric. And if we choose the scalar coupling function for, which couples to the torsion scalar in this form, set the C coupling to 0 and the potential to 0, we find in this teleparallel scalar torsion theory a so-called BBMB black hole with a certain scalar field. It has a problem that the scalar field diverges at the horizon. But more general, such solutions of this form exist, where one gets also scalar fields which are smooth at the horizon, and some even vanishing. Then another interesting class is this one, where we fix the scalar coupling function to the torsion scalar field coupling function to this form. We get this rather weird looking metric component and scalar field. However, when we do here in a power law expansion in 1 over R, this really looks like Schwarzschild plus lower order corrections. Right. And then that there exists so few asymptotically flat black hole solutions can be understood in terms of certain O'Hare theorems, which we formulate, or certain O'Hare theorem for teleparallel gravity theories coupled with a scalar field, which we formulate in the following way. So we consider a scalar torsion theory, which is defined by this f of psi and theta, and we consider that psi has the same symmetry as the background metric. Then we find that there exist no spherically symmetric, asymptotically flat, scalarized black hole solutions when we impose the following constraint on the coupling function. So a polynomial coupling in A, so here, a vanishing C coupling, so this vanishes, and then the scalar potential must satisfy this condition. And then we have 4 cases, and the proof can be done very similar to the O'Hare theorem in metric space-time geometry, in scalar torsion theories, that we look at the trace of the field equations, and we integrate it as well as a scalar field equation multiplied by psi, by a scalar field, and then we get certain terms which must be positive. These are these constraints here, and exactly find that if these terms are not positive or not 0, we cannot get any solution, so we find contradictions. Okay, so very quickly, teleparallel gravity beyond general relativity. There exists a plethora of theories because we have no Lovelock theorem. We have a rich phenomenology. The most prominent models are one parameter new general relativity, f of t gravity, and scalar torsion gravity. This is a bit subjective, surely, because these are the theories I work on. So there are many, many others. I don't want to put one theory above the other. One parameter, new general relativity, is certainly least constrained. For f of t gravity, one can explain inflation, but it has some mathematical self-consistency problems. And for scalar torsion gravity, we find scalarized black holes. And also what we've done recently is to extend this to a teleparallel version of scalar Gauss-Bonnet theory. And also there we find scalarized black holes. Okay, that's it. Thank you for your patience. Very quickly, the conclusion. So I explained quickly how to describe the geometry of a manifold in terms of torsion and tetrads. I discussed the teleparallel formulation of general relativity, and it's interesting that this is possible. So mathematically equivalent, but from the point of interpretation, different formulation of general relativity. I discussed teleparallel theories of gravity beyond general relativity. And I hope I convinced you that teleparallel gravity allows us to extend general relativity to find an improved description of gravity, or to search for an improved description of gravity. We have not yet found the teleparallel theory which cures all the problems I mentioned in the beginning, which we have on the basis of general relativity. Quick outlook. So what we are searching for a lot is exact solutions to the teleparallel gravity theories. For example, there's no axial symmetric vacuum solutions known which generalize the Kerr space-time. We're looking further for interior black hole solutions. Then non-vacuum solutions to describe stars and neutron stars. And we're studying scalarized neutron stars and black holes from coupling to the boundary terms. Then one can study the propagation of gravitational waves like quasi-normal modes. Then the question is this birefringence feature a generic feature, or is it special to this model? And the long-term goal would be, which would be really great, is to derive waveforms numerically, as it's done in numerical relativity, to really compare to the LIGO and Virgo observations. However, this is difficult, since for that we need initial value formulation, a Hamilton formulation, which is mathematically well defined and suitable to put the equations on the computer. This is also work in progress. And then there's a question if we can quantize teleparallel gravity theories more conveniently compared to its metric equivalent. And with this, I'd like to thank you for your attention. And if you're interested in joining one of these endeavors, I'm very, very happy to talk also about collaborations. And let me quickly make some advertisement. I know I'm, yeah. So in summary, we have in Tartu, we have a conference on metric-affine frameworks of gravity, where teleparallel gravity will also be discussed. And last but not least, I prepared an incomplete but quite extensive bibliography here in the end. So with this, thank you for your patience and for staying, and yeah, for all the questions so far.
Thank you very much for the nice talk, Christian. Are there questions?
May I ask one? Just out of curiosity, so so far you basically chose the Weissenberg gauge, in which the spin connection is 0 to do the calculations even in black holes. So I'm wondering, is there any other scenarios in which the choice of other gauge is more convenient than Weissenberg gauge?
Not that I know of. For all the calculations I did, this was most convenient. For these calculations of the most symmetric I mean, if you can, when you look at the most general spherically symmetric tetrad, for example, or the most general homogeneous and isotropic tetrad, you can simplify the tetrad by doing some Lorentz transformation and generate some spin connection. So you can transfer some degrees of freedom from the tetrad to the spin connection and vice versa. And it might be that this is beneficial, but I've never used this.
Okay, thank you.
It's a good idea.
I would like to ask one more question. And you mentioned that there's a ghost problem to the f of t theory.
Yeah.
But if the equation motion is up to the second order, why there's a ghost problem?
Yes, this is not enough. Yeah. So you have some degeneracy in the when you write down your fields, when you write down your equations and go to the Hamilton analysis and calculate the constraints, you get that some of these constraints are dependent on the field value. So depending on which background you choose, your perturbations, your degrees of freedom which are propagating are possibly different. And some people say this is pathological. And you may even think about space-time regions. Imagine you have a space-time region with high space-time symmetry and other space-time regions with less, then your number of degrees of freedom in these space-time regions would be different.
So you mean this ghost is not a Ostrogradovsky ghost? It is the if it is the Ostrogradovsky ghost there, and the equation motion is up to the second order, there should be no problem.
Yes.
Okay. So you mean this ghost means they may propagate in the wrong way, but not.
Yes.
Okay.
Or the number of degrees of freedom might change, and yes.
Okay, thank you.
Are there other questions?
Can I ask a question?
Yeah, sure.
in this model, how do you actually justify the regularity of the solutions? Because it seems that torsions play a key role instead of like the curvature. So this might be a wrong impressions, but it seems like the strength of gravity is not imprinted by the Ricci scalar or any other of curvature scalars in this model.
Yeah, so since we can always translate, I showed you this equation which translate between torsion expressions and curvature expressions. And since in the end we describe a metric, so when I talk about singularities, for the classification, I look at the result, I derive a tetrad. The tetrad has a torsion. The tetrad leads to a torsion. And then I can derive the metric, and from the metric I can always calculate the curvature, and then I can look at curvature singularities.
I see. Yeah, okay. And but so far there's only I see that there's only one model that already describe about the regularity of the black hole. Is there any other model that already also having the solutions for the interior?
I only know of this one, but there may be more.
Okay, thank you.
So you extended the theory first by decomposing torsion tensor into the vector, scalar, and tensor with some special coefficient. Then you extended by introducing zeta extension one parameter. So in principle, can we introduce one more parameter, then it is the most generalization, or?
I mean, here you can look at this. This is the most general quadratic torsion scalar expression with all parity odd, parity even, with only parity even terms. Here, there's this one. But
so
if you are not choosing this combination here of the parameters, where only one free parameter is left, then you get all of these problems that the perturbation theory couples antisymmetric and symmetric modes, and you get strong constraints just from solar system constraints. Yeah, when you do some PPN analysis here.
Mm-hmm. So the extension of the axial coefficient C8, is that more or less quite most general extension, or there can be more?
I mean, so for this, if you want just terms which are quadratic in the torsion, and you want to restrict to this parity even, this is the most general one. But you can write down many more general. You can take higher powers in the torsion scalars, which you can add. And where is this slide? And here you can, for example, add these parity odd terms. And you can take products of the parity odd terms to get something parity even. So there you can play around a lot.
Mm-hmm.
For an overview, some colleagues wrote a very nice review on teleparallel gravity, which is more complete than what I could present you here. There they listed an extensive list, I guess still incomplete, but a very extensive list of theories of the teleparallel gravity theory. This is this review here, Teleparallel Gravity from Theory to Cosmology, which is really very extensive. I could only scratch the surface in this sense in this talk.
Mm. And in the case of the Einstein gravity, in the FR gravity, by taking some special quadratic or something, I'm talking about the Stravinsky model, there we can just understand that by introducing higher Ricci scalar term, it is equivalent to introducing some inflation scalar terms there. So can we understand the inflation without inflation in the GR theory in that similar way?
Yeah, you can do that. You can also here do a conformal transformation and rewrite Legendre transformation in a way that you get instead of an f of t theory, you get a scalar torsion theory. Yeah, this you can do.
I see. Okay, thank you.
Okay, are there other questions?
I'm wondering how many degrees of freedom in the one parameter new general relativity?
Two
Okay.
propagating degrees of freedom.
2.
This is a nice thing. This theory is very, very close to general relativity.
Okay. So only 2 tensor real degrees of freedom.
Yeah.
Okay. Thank you.
Okay, are there
And this
other
is also
questions?
one way how you can put strong constraints on this when you just study the propagation of degrees of freedom in Minkowski spacetime or around Minkowski spacetime. You find, depending on the value of these parameters, you find different numbers of degrees of freedom. Yeah.
I see.
Are there other questions?
Could you comment about the energy conditions of the TGR or whatever?
You mean the energy conditions on the
Yes.
matter?
Yeah.
So they would apply to the symmetric part of the field equations, because they are really, so to say, this the part of which generalizes symmetric field equations. Actually, I'm not aware, but maybe this has been done, about energy conditions, how they relate here to this antisymmetric part. But if you do the Levi-Civita coupling, so you have here no antisymmetric part, then this is simply always 0, and then your energy conditions apply to the symmetric part of the field equations. Because this is your usual energy momentum tensor, the metric energy momentum tensor here, this symmetric part. And usually you fix the energy conditions, like the weak, strong energy conditions. They are constraints on the energy momentum tensor, on the metric part of the energy momentum tensor. So they impose then constraint on this part, on the symmetric part of the field equations. And we saw in one parameter nu GR, for example, in the field equations, that here it is, that we get then some constraint, if we have some meta source here, we get the energy conditions translate into a constraint on the torsion here, if I like, or the combination of curvature, of Levi-Civita curvature and torsion.
Okay, thank you.
Okay, are there any other questions? If not, I would suggest to end the official part of the seminar here, and afterwards we can have a short discussion. So thank you again, Christian, for this really nice talk.
Thank you very much for coming. Thanks for the invitation. It was great.